Hi, my name is Cabrera. I'm a PhD student at Carnegie Mellon, and today I'm going to talk to you about a general purpose evaluation platform that we've been developing called Xeno. So for a little bit of background, as a lot of you have seen by now, evaluating models beyond aggregate metrics is essential for developing responsible ML and AI systems. This is especially important when working on models that could have potential real-world concerns such as biases and safety issues. There are now numerous cases of models that have potential racist outputs or sexist outputs that can have real-world harm when they're deployed. And in a recent study conducted, a survey of ML practitioners, nearly 40% of practitioners mentioned monitoring real-world performance as one of the top 3 challenges that they faced when actually doing AI and ML development. So there are some existing approaches that help people do evaluation and discover some of the issues that these models could have. These include fairness toolkits, robustness check tools, even libraries for doing adversarial attacks. But what we found is that there has been limited adoption of these tools in real-world ML workflows. A lot of these come out of academic centers and just aren't really adopted when people are in the wild building these systems. So we wanted to better understand why this is. Why are they not being used? So we went out and we did 18 need finding interviews with practitioners. These included CTOs of small companies, ML practitioners at large technology companies, kind of across the whole spectrum, to understand what their challenges were with evaluation and why they didn't use these tools. And we found that in general, what practitioners care about is evaluating model performance across real world use cases, the kinds of instances that people are actually seeing day to day. In the end, what they did is kind of an ad hoc process to do this. They would find a couple reports that someone filed, an end user would file, then they tried to validate them in some one-off script or notebook. And then maybe a couple months later would start failing again. They'd have to find that notebook, rerun it. And the existing tools that exist are usually tailored to very specific domains or use cases. Can be really hard to set up and are really hard to reproduce and share. There might be a toolkit for fairness analysis of classification, but if you're working with image data, it might not just work, or it might not encode the types of fairness issues you're seeing. So given these insights, we had a hypothesis. Could we come up with some sort of API interface that can encompass all the diverse types of use cases that practitioners see that their machine learning models are being used for, and encode those in a kind of go-to platform for evaluation? This would have a lot of benefits. You'd only really have to learn one API, kind of like a PyTest for machine learning, kind of like what exists already for software engineering. People could reuse and share these components. You could even include more intelligent features like discovering behaviors of potential use cases, and then you can treat it kind of as a central hub that anybody on a team could use and collaborate on. So the system that we ended up prototyping, given these insights that we had from the interviews, is called Zeno. So before I get into the system design, I want to talk a little bit about the terminology. So we defined kind of a model behavior as a metric calculated on a slice of data, where slice is a subset of data that is a combination of different metadata filters, and metadata is tabular data describing data instances. So a common one you could think of is images, or just kind of pixels, but you can derive metadata, for example, the color intensity of, or the brightness of an image. That would be a metadata column that you could calculate and evaluate on. And our proposal was that by just using this very small core concept of slices, we can encode a lot of the interesting behaviors and use cases that people see in the real world. So what we did for Zeno is we implemented a system that has 2 main parts. Python API that kind of encodes those basic building blocks of metadata and metrics, and then an interactive UI that lets people actually do this behavior analysis and interactively explore, slice, and evaluate their model. The Python API is simple Python wrappers that people can write their own functions and wrap them with these decorators. It has some basic building blocks like what we call distill functions for creating new metadata, transform functions for doing perturbations on instances. And then Zeno takes these functions, runs them through a pipeline, and outputs all of it to the front end. The front end has 2 main parts: an exploration UI, lets people look at instances, interactive filter and slice. Does not require any programming, can be used by any type of stakeholder. Next one is the analysis and testing UI. This lets you take those initial slices of your created insights and actually create high-level reports of how your model is performing. Different types of charge. You can actually even set expectations of how you expect your model to perform and get alerts if it's falling under, say, a certain threshold of accuracy. It's kind of your high-level summary of how your model is performing. I want to show a quick demo and overview of how the system looks. This is the Explore page, which is the main landing page. It has two parts. On the right, we have the instance view that lets you kind of explore your data and the model outputs. On the left, we have the metadata view. So the instance view, you can kind of click around on, paginate. This is a modular view that works for a bunch of different types of data. And on the left, you have the metadata. So here we can, for example, click on different classes and it interactively filters our data. So we can see, for example, that the performance might be lower for certain classes than others. It's also colored by the accuracy to make it very easy to see. Here, we actually filter on a column that we created using a distill function, which generates new metadata. So we wrote a function in Python that calculates the brightness of our images, and we can actually compare, for example, the high brightness images have maybe a 63% accuracy for this model, while the low brightness have a pretty low accuracy of 56%. So if you find a subset that you care about, for example, maybe we care a lot about images that have a high red value. Maybe we've seen that those fail a lot in the past. We can select them and actually formally track them as a slice. So here we have a little simple filtering interface where we can select the different predicates we have, like the red count, and filter by it. And then if we scroll up here, we will see that it gets saved in the slices panel for future analysis or for use in the reporting page. In the reporting page, we can create different types of visualizations that summarize the performance of our models in a more quantitative way after we've created slices and found interesting instances in the Explore page. So in this case, we've created a simple bar chart that has slices across the x-axis, a metric, in this case F1, on the y-axis, and actually has bars for each different model that we're analyzing. So here we can see that our model across these different, our models across these different slices do better on average and high brightness images and worse on low brightness images. And this is a pattern that holds across the different models that we're evaluating. And Xeno has different types of visualizations we can look at. For example, this table view that give you different insights into how your models perform. So that's a quick overview of the Xeno front end. It works across a bunch of different modalities. The instance view is very general and give you some interesting insights about how your models perform. So to understand whether Xeno can actually generalize across, can actually work across all these different types of data and models, we conducted 4 case studies with practitioners who actually use Xeno in their own day-to-day models that they either work on or audit or evaluate. These included a researcher creating a model to classify screenshots of UI images, a researcher who was trying to improve a breast cancer classification model, a researcher that came up with a new algorithm to detect which speaker out of a group of speakers someone's speaking to, and an image generation model like DALL-E or Stable Diffusion. And overall, we found that Xeno did help them find interesting and new behaviors. For example, in the breast cancer classification model, we found that the model performed much worse for people with denser breast tissue, which is a significant issue that radiologists, real human radiologists, also face. Or that image generation models often tend to create more explicit images for prompts containing girl or women versus man or boy. So there's maybe some sexual biases imbued in the models that we're training. We also found that the API can very easily integrate into common workflows. All these different practitioners use different libraries like PyTorch, Keras, or PyTorch Lightning that were very incompatible, but since they're in Python, they work well in Xeno. Additionally, we found that there are some areas for future work that could significantly improve the process. For example, given these building blocks, we could actually imbue some more intelligence into Xeno to automatically discover new slices, for example, that might be underperforming, might be interesting use cases or behaviors. We might consider ways of automatically improving and fixing some of the issues that we see. And we might think about Xeno scales reasonably well to millions of instances, but a lot of data sets might scale to 50 million or 100 million plus instances. So there's some room for improvement in improving Xeno. So in sum, Xeno is a general purpose model evaluation platform that we think can be a very simple yet generalizable paradigm that can be used to really understand these models beyond simple metrics such as accuracy and create the next generation of responsible AI systems. Thank you very much.